Okay, so hello everyone. Today we'll talk about the Radix Sort. Actually, the lecture is not like totally focused on a Radix Sort, but more about the approach that Radix Sort brings and the things around the Radix Sort. And mostly we will talk about the non-comparison based algorithms, non-comparison sorting algorithms. So today, first we will talk about what is the comparison-based algorithms. Then we'll talk about what is stable sorting algorithms. Then after these two topics, we come to the conclusion what is non-comparison-based algorithms, and then we'll talk about the three algorithms that use this approach of non-comparison basing, non-comparison of the elements in the array. So let's get started. So first, what is the comparison-based algorithm? Comparison-based sorting algorithm. Comparison-based sorting algorithm is algorithms that compare the elements between each other in order to sort the array or input. So far in the previous semester, we already covered these algorithms like a merge sort, quick sort, insertion sort, selection sort. All these algorithms, they all sort, first of all, and second one, they sort it by comparing the elements between each other. And here is the lower bound of the merge sort. The lower bound of the merge sort is n log n. Lower bound is of the quick sort also n log n. Lower bound insertion and selection sort it's n squared. Of course, this is not full list of the comparison-based algorithms. As you can see here from the lower bounds of these algorithms, there is no algorithm that runs faster than this n log n lower bound time complexity. And the reason that there is no such kind of algorithm is on its nature of sorting. And the nature of its sorting is, as it says, comparison based. When we sort some algorithm, and if that algorithm is based on comparison, there is no other way to run them faster than this. So let's see why it cannot run faster than this time complexity, and here is a proof. Let's say that we have just a very simple array of 3 elements, and here in the first element is the 6, second is 8, and the third element is 5. If we take this array and if we will try to sort the permutations that we can get from this array can be shown in this tree. This is a decision tree, and in this decision tree, each leaf represents one permutation of this array. Of course, this the solution for this is like this. Here is it colored with the black here, each edge, and this is a sorted array of our initial array, and these other leaves, they are results, like other possible results of our sorting. And as you can see, if we have 3 elements, then the number of leaves that we can get is equal to the 6. So here we have 6 leaves. This is a binary tree, and the number of leaves is based on a 3 factorial. We have 3 elements, and the 3 factorial is equal to 6. So how can we prove that our comparison-based algorithms cannot run faster than n log n. As you can see, the solution is based on the height of this tree, and the height of this tree is 2 power of h. H is height of the tree, and we cannot run lower than n factorial. We cannot find the solution less than the number of leaves here. And here is if we apply this rule, we can prove that our comparison-based algorithms cannot run faster than n log n. For more detailed explanation, you can tomorrow visit the lecture, and we will talk about in detail about the proof. Right now, you can just take a look at this proof, and as you can see, it says big omega of n log n. Next, it's a stable sorting algorithm. So actually, the stable sorting algorithm is kind of mix of it can be at the same time like the algorithm that is stable sort. They can be also comparison based, and some other algorithms is also is non-comparison. So stable sorting algorithms are the algorithms that after the even sorting, they preserve the relative order of equal elements. For example, let's say that we have this kind of initial array, and after the sorting, this duplicate numbers like 8 here. The 8 that was before in our initial array. After the sorting, it stays before the other 8. This is the stable sorting types. And in unstable sorting, after applying the sorting algorithm, the 8 that was before the another duplicate 8, it stays after this 8. There are some algorithms that after the sorting, they still preserve the relative order of equal elements, and there are some algorithms that doesn't preserve it. So non-comparison-based algorithms. Non-comparison-based algorithms, they're based on a non-comparing. They're based on using other techniques like some bucket or counting the elements, and based on that approach, they sort the array. But these non-comparison-based algorithms, they run on some assumptions. Like we need to know some information about the input before sorting it. Like usually, these assumptions are that the input numbers are between 0 and some number k. So first, let's talk about the counting sort. By the way, non-comparison-based algorithms are counting sort, Radix sort, and bucket sort. So first is the counting sort. Counting sort assumes that each of the n input elements is an integer in the range of 0 to k for some integer k. When k is equal to big O of n, then sort runs in big theta of n time complexity. So there are three main elements in the counting sort. First one is the array, input array, like the array that we need to sort, and let's call it array A. And n is the length of that array. Then we have sorted array, the results of our sorting, where we will store the elements in a sorted way. And third array, it's a temporary working storage, where we store some temporary results or temporary additional information, and we call it array C. And the range of the array C is between 0 and k. K is the number of the maximum values that we have in our initial array. N is the number of elements in our array. So what are the steps of the counting sort? The first one, we count the number of each element and store it in array C. Then count the number of elements less than or equal I and store it in array C. Then we put the elements into our result array B. So here is the pseudocode of the counting sort. First, here is, as you can see, A is our input starting array, the array that we need to sort. B is our result, and K is the maximum value that we have in array A. So first we initialize array C, and we say that array C has length of K, and for each element, for each index, we say by default that the result is 0. So we have the first for loop that runs between 0 and K. Then we have the next for loop that runs from 1 till the up until the n, which is n is the length of our array A. Then we here in this part of the code we just compare, like not compare, just count the like number of appearance of each element in our array A, and we store that result in array C. On next step, we have the for loop that starts from 1 and runs up until K. In this part of the array, we just compare, we like count all the elements before the I. And on third for loop, we just run the from the n up down till the 1. And here we say that in a B we store the element that based on our array C. So here is the time complexity of the counting sort. This part of the code takes big O of K because it runs from 0 to K. This part of the code runs from 1 to n, so n is the length of A. This part of the code runs from 1 to K, and this part of the code runs from n to 1. So that's why it's a big total of n. So the overall time complexity is big theta k plus n. Actually, in practice, it's a big theta of n because k is usually less or equal to the n, and like it runs by dominant, and usually it's big theta of n. So how does the counting step sort work? So first we have the array A. As you can see, this array is not sorted, and K here actually equal to the 5. 5 is the biggest number in our array. So we create the array C with the size of the K, with the size of the 5. So here is we have the array C with the size of the 5, and on the first step we count how many elements, like the number of frequency of each element, and under each index we store how many elements of, like, what is the frequency of each element. For example, as you can see, 0 we have 2 times, here and here. So that's why we, under the index 0, we put 2. We don't have any element with the value of 1, that's why this stays 0. We have 2 elements of 2, this one and this one. That's why under index 2 here we put 2. Then we count the 3. Here it's 1, 2, and 3. Here we write 3. The 4, we don't have 4, that's why we put 0. And we have 5, and the 5 is only 1, and that's why we here write 1. So this is step number 1. Step number 2, we count the number of elements less or equal to I. So we count all the elements less or equal to I. So that's why, for example, we keep that record in the same array C. So in order to count the number of elements less than or equal to I, we count 2 plus 0, it's 2. Here we write 2. So it means that the number of elements which are less or equal to I, which is here, I is the index, is equal to the 2. So we have 2 elements that is less or equal to the I. Then we can find the number of elements that is less or equal to the 2. And as you can see, we have 2 zeros and 2 2's. So that's why here we put 4. The number of elements that is less or equal to I is equal to the 7, because 2 zeros, 2 2's, and 3 like elements with a value of 3. And here we say 7, then on the index 4, here it's 0, that's why we take this value, which is 7. And here the number of elements that less or equal to I, which is a 5, is equal to the 8. So this is step 2. After the step 2, our array changes to these values. Then on step number 3, we put the elements into our result array, which is the array B. And if we take a look on a pseudocode, so here is a pseudocode. In the pseudocode, the third step is this one, like line 10, between line 10 and line 12. And as you can see, our for loop starts from the back side of the A. It starts from the N and goes down to the 1. So here, our initial array is this one. So we start from the back and we see that we have 3. So we take 3. Here we take 3, and as you can see, it shows 7. It means that we need to put this 3 into the position of 7. Here we put 3 here, and we subtract 1 from the index of the 3, and it becomes 6. Then, as you can see, we have 0. So we take a look on our array C, and we see 2. So here on the index 2, we write 0. And we subtract 1 from the 2. And here we have 1. Then we have again 3. So we again take a look on the 3, and we see that it's 6. So our next element should be under the index 3. So here it should be here. Then of course we subtract from 6 1, and it becomes 5. And we keep doing that up until we go through the whole array, and in the end we get this kind of result. So what are the properties of the counting sort? Counting sort is, first of all, is a stable sort, because if you take a look on the result, you would see that the duplicate numbers, they keep their relative order. For example, here we have 3 3's, this 3, this 3, and this 3, and the first 3 stays the last one, because here it stays 7. Then this 3 goes to the position of 6, and the next 3 would go to the position of 5. Here it would stay here. So the duplicates save that its relative order. And the next one is the time complexity. The time complexity of the counting sort is big theta of n, which beats our lower bound of big omega of n log n time complexity. So this counting sort runs faster than other comparison-based algorithms. So next we'll talk about the Radix sort. The Radix sort is also a sorting algorithm that's based not on comparisons but based on sorting the digits of the integers. So it starts from the sorting the least significant digit, then sorts the second least significant digit up until we have the most significant. So in short, it starts from the least and goes to the most significant digit. So let's say that we have this kind of array, and first we put we sort the elements based on least significant. For example, here the least significant is these numbers. And after sorting on a least significant, we got this kind of result. Then we have the next least significant is this one. And based on that, we got this result. And in the end, we got to the most significant. And based on that, we got this sorting algorithm. So here is the pseudocode of the Radix sort. Actually, Radix sort is just sorting algorithms that just focus on digits. But how to sort? It should be used some like auxiliary sorting algorithm, and usually it's used as used counting sort. Here in a Radix sort, we need to use the stable sort, one of the stable sorts, and one of the stable sorts are the counting sort. And as you can see here, if we use counting sort, then the time complexity of the Radix sort big of d multiplied n by plus k. Actually, this n plus k is the time complexity of the counting sort, because the sorting of each digit is used by counting sort, and we have, let's say, d number of digits, then we need to do d times of counting sort. So this is the time complexity of the Radix sort. And next is the bucket sort. So what is a bucket sort? Bucket sort assumes that the input is uniformly distributed, and if our input is uniformly distributed, we can reach the time complexity of the big N. Of course, if our input is not uniformly distributed, then the time complexity is different. It's not big of N, it's much worse than that. And the bucket sort also uses some auxiliary additional sorting algorithm to help sort the numbers. So how does the bucket sort work? So let's say that we have array A. Here we have some numbers, and based on that we can say that we have 9 buckets, and we put into each bucket based on which range each number belongs to. So for example, for the tens, here we have bucket for the tens, we put this number and this number. Then for bucket of 20s, we put this number, so for this bucket, and this number and this number. So after putting each number to its own related bucket or interval, we need to sort this number inside of these buckets. each bucket should be sorted individually. And the sorting algorithm that used for sorting these uh, elements inside of the bucket is insertion sort. So as you know, insertion sorts the time complexity is big of n square. So, but if we would have only one element for each bucket, we would we wouldn't need to use the insertion sort, and we would just need to spend the time in like for the putting the elements into the bucket, and in that case our time complexity would be big of n. But if our elements are not uniformly based, then we need to spend a lot of time on sorting each bucket, and the sorting each bucket takes n square, and then the time complexity would be like this one if our numbers are not uniformly distributed. So here is the conclusion of today's lecture. Comparison-based sorting algorithms, they cannot break the big omega of n log n time complexity, because the model of the comparison-based algorithm doesn't allow us to do that. Anyways, we need to compare the elements, and it takes time. That's why we have non-comparison-based algorithms, which helps us to break this like a border, and it helps us to run much faster than this time complexity. The Radix Sort is not just one pure algorithm. It needs assistance of other stable sort algorithm, and usually that stable sort algorithm is counting sort. Bucket sort also requires other sorting algorithm, which is insertion sort, for sorting the elements inside of the bucket. So in a pure, this Radix sort and bucket sort, they not used like um, in a pure form. It needs some mixture of other sorting algorithms. But still, the Radix sort and bucket sort, they are like, the main idea is that they are not comparison based algorithms. They are not comparison based algorithms. So for today's readings are from the book of the Kuhlman, Lasers and Levi Stein, chapter 8. Good luck. Thank you very much for watching. Bye.